Hello, everyone, and welcome back to Week 3 Monday. So, that video on intermolecular forces got a little lengthy. I apologize for that. At least on YouTube, you can watch me at twice the speed. Here's your second chunk of information that I'm going to talk about for what I'm calling Week 3 Monday, and that is really going to be focused on the Clausius Clapeyron equation. But we got to do some stuff to get there first. So, we are going to look at the delta H of phase changes. Remember, let me get my pens going. Remember that the delta H is the change in enthalpy of phase changes. Right now, we can really just think about this in the change in energy. There's a difference. Chemists and physicists, we argue about what does energy mean a lot of different ways. And towards the end of this class, we're going to get more and more into like what real energy talking about is. For right now, we can really just think about this as a change in energy, the delta H of phase changes. We've done this before. I'm not going to spend a whole lot of time talking about it. We did it last semester. Remember, and this is going to bring back some guttural tears, I am sure. Remember these looking diagrams? And I like to put ice cubes into hot beverages and so on and so forth. And I like to calculate how much energy it would take to melt ice and so on and so forth. We already did these delta H's of phase changes. So remember, when a substance goes from the solid phase to the liquid phase, that would use the delta H of fusion. The amount of energy it takes to melt a substance is the delta H of fusion. The delta H of fusion, when you go from solid to liquid, is positive. It's an endothermic process. Energy is required. And going from liquid to solid, you would use the negative delta H of fusion. That's an exothermic process. Energy is released. So you would need to change the sign on that. So how much energy does it take to melt a sample is the delta H of fusion. Well, what we care about this time around, though, is what happens when you go from a liquid to a gas. That phase change is called vaporization, and it uses the delta H of vaporization. That is an endothermic process. When you go from liquid to gas, energy is required. So if energy is required, that is endothermic, and so that's positive. And of course, going the opposite direction, you would just use the negative delta H of vaporization because that is an exothermic process. Energy is released. Delta H is a negative. So we want to know really what is happening with this delta H of vaporization. And the vapor pressure, just in case, and I mentioned this in the last video as well, but VP is the vapor pressure. And we want to know, how does the vapor pressure change above the surface of the liquid? What we learned about last time was that if a molecule has a strong intermolecular force, so strong intermolecular force, we're talking about like hydrogen bonding, or it's a really noodly molecule that just has the London. If it has a strong intermolecular force, it's going to take way more energy to get it up into the gas phase. So the delta H of vaporization is large. Lots of energy required to change the phase. More tightly held together two molecules are, the more energy is required to get it to undergo that phase change. So its delta H of vaporization should be large. And if you have that strong intermolecular force, you should have low vapor pressure. Again, the vapor pressure is basically the amount of vapor above the surface of the liquid. If a molecule evaporates very, very, very readily, it's going to have a higher vapor pressure. I have to sneeze. Sorry about that. If a molecule is not held very tightly to its neighbor, it's going to evaporate very easily. It's going to have a low delta H of vaporization, and it's going to have a ton of molecules in the gas phase above it. Nothing's going to stop those two molecules from separating, and they're going to go into the gas phase. However, if those molecules are held together really tightly, then there's not going to be a lot of molecules in the gas phase. Because again, the difference in the liquid phase, you have two molecules and they're interacting with each other. That is what's happening in the liquid phase. When energy is put in and those two molecules separate, you pull them apart from each other. You break the attraction between. Now they can go into the gas phase, because in the gas phase, the molecules don't interact. They're moving around really, really, really rapidly, not interacting. And so in order to separate if you have to put in a lot of energy to separate two molecules, they're not going to be a whole lot in the gas phase. They're going to stay in the liquid phase. If you can separate two molecules really easily, then they're going to go up into the gas phase. It's like the boyfriend and girlfriend who are like really, really committed to each other. They're not going to be separated from each other. They're not going to be off in the gas phase doing their own things and not interacting. Compare that to two people who don't even really like each other. Well, if those two people who don't really like each other are still in a relationship together, they're going to be doing their own thing all the time. It's going to be easy to get them to go into the gas phase because they are not strongly held together. All right, so let's see the impact of temperature on vapor pressure. So I'm going to have two test tubes. And in this test tube, I'm going to have some liquid at room temperature. That is what RT stands for. I think sometimes I forget to abbreviate it for people or tell them what the abbreviation is. We have a room temperature sample. I want you to tell me, how is that going to be different in terms of the vapor pressure? How different will it be, the amount of vapor pressure? And again, like, I'm using these terms that are not actually precise, right? Like pressure is, pounds per square inch. It's a millimeters of mercury. It's like how rapidly molecules are hitting the walls of container. That's what we've learned about pressure. And I'm kind of changing my language about it right now, and I'm just saying how much. So really, I'm just saying for these purposes, we can talk about the vapor pressure as being just how much is there. So how much vapor do we have above the surface of a liquid at room temperature compared to the same liquid at high temperature? So this is my gas. I'll give it some yellow highlighter flames. So this is at high temperature. Which molecule is going to have larger vapor pressure? And hopefully you guys know it's going to be the high temperature one. At high temperature, more molecules will be in the gas phase. Which leads to a higher vapor pressure. You've got more molecules up there, they're going to be exerting more force. So, this gets us into the definition, the real true definition of boiling point. The normal boiling point of a liquid is the temperature at which the vapor pressure is equal to 1 atmosphere. This is definitely something that you should get to know, because I use it kind of as it's a little bit of a trick. I'll be honest. It's a little bit of a trick, and I'll point out like where I use it and how I use it is a little bit of a trick. But the normal boiling point is the temperature at which the vapor pressure is equal to 1 atmosphere. Just a boiling point, not normal. That word that's important on this is the word normal. Boiling point. To this point, really, we've just been talking about boiling point is the temperature at which it undergoes the phase change. Not technically true. Because if you think about it, water boils at different temperatures based on altitude. So if you've ever been like making a box of like brownie mix or something, making like cupcakes in your house, if you turn it over, it'll have high altitude directions. And you have to do different stuff to your baking in order to get it to bake properly at high altitude. And that is because water's boiling point at high altitude, and I'm talking about like in Denver. I've just had mega flashbacks. I'll tell you about that in a second. The water's boiling point at high altitude is less than 100 degrees Celsius. Because the boiling point is not just the temperature at which it undergoes the phase change. Boiling point is the temperature at which the vapor pressure equals atmospheric pressure. How much or at what temperature do you need to put in there so that the amount of gas you have above the surface matches the amount of pressure the atmosphere is pushing down on you? You've kind of got this like balancing act going on. And if you've got a high pressure pushing down on you, the boiling point is going to be greater. You got to have more molecules in the gas phase to like overcome that atmospheric pressure pushing down on you. As opposed to like in Denver. In Denver, because of the altitude, the pressure is less. If the atmospheric pressure is less, then you need less energy to get the molecules to go into the gas phase. So that's why we have this concept of normal boiling point. That's just taking it down to 1 atmosphere. All right, and I'll explain again some more about that as we continue. Now, the issue is we can measure this, all right? We can calculate how much vapor pressure there will be at certain temperatures. And my friends who want to be engineers, whew, this is engineering. Because like engineers like design systems and stuff like that, and you need to know how much pressure your system is going to have. And so this is engineering at its core. Now the problem is though, so calculating the vapor pressure of different liquids at different temperatures, not linear. It increases logarithmically. So here is ether. And you can see as the temperature increases, the vapor pressure increases, but it's not just linear. So linear would look like this, okay? This gray thing, that is a linear line. You can see, however, that this this ether is curved up, not linear. You can see water is curving upwards, not linear. And mercury is also curving up, not linear. So that means, my friends, we get to use natural logarithms. Dun, dun, dun. So, sorry, I'm getting really into this. I go a little crazy when I'm alone in my office, like talking to myself. So, here are 3 different calculators. I just want to point out where the natural logarithm button is, because the natural logarithm button is super, super important to us. So this is my favorite calculator, the TI-89, although right now I'm using a TI-84 Plus. But anyways, it's right here. So you see this, you would hit the second button and then this key to go into natural logarithm. You would hit the green button and this key in order to go into e to the x. We're going to need that. Here is another calculator, TI-83, my second favorite calculator. You have natural logarithm right there. You just hit the button. And then you have e to the x. That would be second natural logarithm. And then last but not least, this is another calculator I've seen a whole bunch in my day. The natural logarithm button is there. And e to the x is you would second natural logarithm to get e to the x. You need this, okay? So I don't know what you guys are using for calculators, but natural logarithms and logarithms base 10 are going to become important in 1520. So know where your logarithm and e to the x button are. I'm just going to do like the briefest introduction to natural logarithms just so we can think about it, like divorcing it from chemistry. Let's think about it in purely mathematical terms so that when I actually put chemistry terms to it, it's less tricky. Easy. What is the natural logarithm of 3? Literally and truly, and you'll hear me say this a bunch. The natural logarithm of 3 is just a number. You just put in on your calculator natural logarithm 3, close parentheses, enter, just a number. So that's what you're going to hear me say a lot. The natural logarithm of a number is just a number. What is the difference? There's no variables in the terms of the natural logarithm. The variable is over here. So when the variable is on the right, when there's just a number in those parentheses, the answer is just a number. So again, take a second, pause, pull your calculator out so you can figure out what the natural logarithm of 3 is. The answer is 1.099. Just a number. That is good enough for us. Now, here's a harder one. The natural logarithm of x is equal to 2. What does x equal? We have to undo the natural logarithm. So this is what I say. We have to undo the natural log. And how you undo the natural logarithm is you take e to the power of both sides. Again, I don't know how mathematicians talk about this. If you need help on your natural logarithms and undoing natural logarithms, talk to a math professor. I am not the right person to talk you through the math of this, but you have to undo the natural logarithm by taking e to the power of both sides. E to the power of the natural logarithm of x. E to the natural log just goes away, and you're left with x equals. And then we're going to bring this side down. X equals e squared. So again, that's where you look at your calculator and you find that e to the x button, and you want e to the second power. E to the second power is 7.39. So again, when the variable is in the parentheses after the natural logarithm, you undo it by taking e to the power of both sides. And last but not least, super hard natural logarithms. What is the natural logarithm? The natural logarithm of 1 over x is equal to 5. Let us solve for x. And again, if I were doing this in class, I'd pause, give you some time to work on it. As it is, I'm just going to keep going. So here's the thing. So my thought process. The variable is in the natural logarithm. That means I'm going to have to undo it. It's not just a number. It has a variable in there. So I'm going to take e to the power of both sides. E to the natural log gets rid of it. So I am left with something I was about to write incorrectly. 1 over x equals e to the 5th power. E to the 5th power is just a number. So you get 1 over x equals 148.4. And now we've done this last semester. You can either take both sides to the -1. I don't care if you do it that way. But if you're like, wow, that makes no sense, what you get is 1 equals 148.4x. I multiplied both sides by x to get x out of the denominator. Then I'm going to divide both sides by 148.4. X is equal to 0.0067. So again, if this is hard, pause here and get some help before I start showing you the chemistry part of things. You need to have a basic understanding of natural logarithms and undoing natural logarithms in order to do the chemistry. All right, so this is just a review slide. I'm sorry, I was supposed to delete it. We're talking about boiling point. Boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure. Elevation impacts it by the higher up in altitude. I'll write this down just in case. The higher up in altitude you go, like if you go to Denver, I'll tell you my story about Denver. If you go to Denver, it's the mile high city. So if you go up in altitude, that means that the atmospheric pressure lowers. You're closer to the vacuum of space, is what you can think about it. So if you're closer to the vacuum of space, you're going to have a lower atmospheric pressure, which happens in Denver. And if you have a lower atmospheric pressure, the boiling point is going to be lower because, again, it is the temperature at which the vapor pressure equals atmospheric. So if you have a lower atmospheric, then you're going to have a lower boiling point. Normal boiling point, on the other hand, we're just setting it equal to 1. So we're just pretending that we're at sea level. So my story about this is I have a friend who lives in Denver, and he came here to visit once, and he is a coffee snob, like crazy coffee snob. He brought his own coffee and everything. I'm pretty sure that he has a travel coffee maker now that he travels with because when he came to see me, at least my coffee maker wasn't good enough for him. Anyways, he made coffee for himself at my house with his coffee maker. And I was like, "Oh, how's your coffee?" And he's like, "This is terrible." I was like, "What the hell? What's going on?" He's like, "Oh, we're not in Denver. We're closer to sea level. The water has a different boiling point." And he was claiming that the boiling point of the water really impacted the taste of the coffee. Oh, so pretentious. Anyways, that's my story about Denver. So, here is the Clausius Clapeyron equation. It is a doozy. So I'm going to take you through it piece by piece. The bottom line, the Clausius Clapeyron equation gives you the relationship between temperature and vapor pressure. So let's walk us through it. We have the natural logarithm of pressure in instance number 2. Okay, what we're really doing is we're looking at a sample at 2 different temperatures and what the vapor pressures are at those 2 different temperatures. Remember, it's the relationship between temperature and vapor pressure. So this is the vapor pressure at this temperature. And this is absolutely the most important part about getting the Clausius-Clapeyron equation correct. Making sure that whatever the vapor pressure is that is on top in the natural logarithm part matches the temperature that comes first in the 1 over T2 minus 1 over T1. So P2 on top, T2 in the first place. And then we have P1 on the bottom, T1 in the second place. That has to be the same. So we're talking about 2 different temperatures, 2 different vapor pressures, and how they're related to each other. So then the other part of this is we have the negative, don't lose the negative sign, delta H of vaporization, and we have R. Now, most normal people would say to me, well, R is equal to 0.0821 liter atmospheres per mole Kelvin. And that's true. That's the gas constant. Here's the problem though. Our vapor pressures, P2 and P1, those are going to be in atmospheric terms. And what I mean by that is they could be in millimeters of mercury, it could be in torr, it can be in atmospheres. It's just going to have normal pressure terms. I guess that's a better word rather than atmospheric terms. So it's normal pressure terms. Millimeters mercury, torr, atmospheres. Delta H of vaporization is almost assuredly going to be in terms of either kilojoules per mole or joules per mole. Now, the problem is if we look at our R that we said that we know, 0.0821 liter atmospheres per mole Kelvin, there's nothing in there about joules or kilojoules. We can't use this because our delta H has energy terms in it. So here is your new R. R in energy terms is 8.314 joules per mole Kelvin. All right. So now we have it in energy terms. And if our gas constant is in terms of joules, we have to make sure our delta H of vaporization is also in terms of joules because they have to be able to cancel. So this is where I want you guys to think back to like the Rydberg equation way back when we learned in 1510. And I was really starting to emphasize units to you guys. And the big thing about the Rydberg equation is nanometers versus meters. You can't put in a wavelength in nanometers because the constant is in terms of meters. Same thing here. You have to make sure that the units on all of your stuff matches the units of your constant. Our constant is 8.314 joules per mole Kelvin. So we want our delta H to be in terms of joules per mole. And then last but certainly not least, we have our temperatures. Our temperatures must be in Kelvin because again, our gas constant is in terms of Kelvin. So we have to make sure that that stays the same. So use the units on your gas constant to tell you what the units should be for all of your other stuff. So here we go. Let us just jump into this. I have not solved this this year yet. So we are going to have some fun and figure this out together. What is the vapor pressure? I'm going to color code this in blue. Okay, so we know we're going to be solving for that. And we're solving for the vapor pressure at 113. Just for no reason, I'm going to say that my P2 is going to be what I'm solving for. And my T2 is going to be that 113 degrees Celsius, of course, converted into Kelvin. So I'm going to start my list here. I'm going to say P2. Now, I don't know what it is. What is the vapor pressure? That's what I'm going to solve for. T2, they have to be at the same. Like I'm looking for the vapor pressure at 113. So I'm going to say that T2, because it's the same instant, is 113 degrees Celsius. And I'm going to convert that into Kelvin. So 113 plus 273.15. 386.15. Okay. If the liquid has a delta H of vaporization of 35.5 kilojoules per mole. All right. I know where it's going to go. I know that the delta H of vaporization is 35.5 kilojoules per mole. I'll come back to that in a second. And it has a normal boiling point of 122 degrees Celsius. That's giving me my P1 and my T1. Now, it doesn't look like I've given you a vapor pressure. But remember, normal boiling point is the temperature at which the vapor pressure is equal to 1 atmosphere. So this is the trick to it, or this is the it doesn't look like I'm giving you enough information. Normal boiling point is the temperature at which the vapor pressure is equal to 1 atmosphere. So we have a P1. And again, just arbitrarily, that could have been P2 as long as the P and the T are at the same time. So the P2 goes with what's in front and the P1 goes with what's second. It doesn't matter. I'm just arbitrarily saying P2 is what I'm solving for. It does not matter. P1 is 1 atmosphere because it's the normal boiling point. And at T1 is 122 degrees Celsius plus 273.15, converting it into Kelvin right away. 122 plus 273.15. Oh, that is a typo. 122 plus 273.15. 395.15. Okay. Okay. And then that just leaves us with R. Let's give it green. We know what R is. R is 8.314 joules per mole Kelvin. Double check. Make sure your units make sense. The first thing I'm going to say is, okay, well, my P1 is in terms of atmospheres, so that's going to pop out my P2 in terms of atmospheres. They're divided by each other. As long as they have the same units, they're going to cancel. So if P1 is in atmospheres, P2 is in atmospheres. My gas constant is joules per mole Kelvin. All right, so moles is fine, that matches. Kelvin is fine, that matches. Joules and kilojoules do not match. We have to convert. Every 1 kilojoule is 1,000 joules. Don't forget this. All right. This is definitely a place that I get people who forget and who do it in their head and get the wrong answer. You multiply. This is 35,500 joules per mole. Now, all of my units match and make sense. Joules to joules. Now we got to do algebra. Are you guys ready for algebra? Here we go. The natural logarithm of X. That's the vapor pressure at 113. I'm labeling that as X. Divided by 1 atmosphere. And again, I'm leaving the units out just to simplify the math. You can leave them in if you want to, but I am taking a shortcut. Because I've double checked all my units on the left-hand side, I'm not putting them into the equation. So we have the natural logarithm of X, that's what we're solving for, divided by 1 atmosphere equals negative 35,500 divided by 8.314 times 1 over T2, that's at 113, so 386.15, minus 1 over T1, 395.15. My friends, if you get to this place, you are over halfway there. All right, over halfway there. I'm going to walk you through how I do the algebra. And again, I know I do algebra weird sometimes because I get afraid of negative numbers and stuff like that. So however you want to solve it is however you want to solve it. I don't care. This is the way I see it. X divided by 1 is just X. So we have the natural logarithm of X. This is another place that I'm thinking to myself like, oh man, I'm going to have to undo it. The variable is in the natural logarithm. So the term after the natural logarithm, what's in the parentheses is the variable. I'm going to need e to the. So I just got that in the back of my head. Now, negative 35,000 divided by, negative 35,500 divided by 8.314, just a number. On my calculator, negative 35,500 divided by 8.314 gave me negative 4,269.9. And I'm keeping digits. I keep lots of digits until the end. And then over here on my calculator, 1 divided by 386.15. That is a typo. Try again. 1 divided by 386.15. Enter. I'll just write it down. 0.0025897. Don't lose a lot of digits, okay? So I'm keeping a lot. You can leave it on your calculator. I don't care. But that's going to be minus 1 divided by 395.15, which is 0.0025307. Hopefully you guys can see why I need all those digits. They're not the same. You can't just go to 0, okay? So you need to keep lots and lots of digits for you. On my calculator, rather than splitting it into 2, I would do 1 divided by 386.15, and I would just keep all of those digits minus parentheses 1 divided by 395.15. Close parentheses, enter. I got the natural logarithm of x is equal to negative 4,269.9 times 5.8983 times 10 to the negative fifth. So again, don't round. If we rounded that to 0, we would be in a world of hurt. It is not roundable. You have to keep all of the digits until the end because it's going to be, it's just, it makes a big difference. So don't round too much in that. All right, now I just multiply those two things together. So we have the natural logarithm of x equals that number times negative 4,269.9, negative 0.25185. Again, you can see if we had this value and we were just like, oh, it's basically 0, it's not. Because if it were 0, then this would be 0, and it's not, okay? So just be careful with your roundings. Now here's the tricky step. We're going to take e to the power of both sides. E to the natural logarithm of x, you're left with x. And on my calculator, I'm going to put in e to the, and I'm just going to hit e to the answer because it's still in my calculator, right? Like it's like saved because I'm using, I'm using my phone, but it's basically a TI-83 is what I have downloaded on my phone. So I have e to the answer, and I get x is equal to 0.777, and that is in terms of atmospheres because we were solving for a vapor pressure. So what is the vapor pressure at 113 if it has a vapor pressure of 1 atmospheres at 122? So we already know it should be less. We are less than 122, so our vapor pressure should be lower. We haven't put in enough energy to get as many molecules into the gas phase. So, sure enough, 0.777 atmospheres is our answer. All right, guys, that is the Clausius Clapeyron equation. Let's do one more, okay? I think before I send this out to the wonderful place of YouTube. What is the delta H of vaporization? Oh, good Lord. Okay, so we already know what we're solving for. Of a liquid with a, and I'm going to put this in pink, normal boiling point of 95.6. So again, what that means is we have 1 atmosphere at 95.6 degrees Celsius. Normal boiling point. The vapor pressure equals 1 atmosphere. Then I'm going to switch to, I think I've been using blue, a vapor pressure of 621 millimeters of mercury at 85.2 degrees Celsius. So again, that goes together. And again, it doesn't matter. I'm trying to see. I can put blue at the bottom as long as the vapor pressure is at that particular temperature. So I'm going to want this 621 millimeters of mercury. Just give me a second on that, all right? I'm going to label that as P1 is 621 millimeters of mercury at T1 of 85.2 degrees Celsius. We're going to come back to that again in a second. And then the other variables, we have the P2, that's 1 atmosphere at 95.6. So P2 is 1 atmosphere at T2, 95.6 degrees Celsius. Delta H of vaporization is what we're going to solve for. Don't lose the negative sign. That negative sign is crucial. And we know that R is 8.314 joules per mole Kelvin. Okay, so before we start shoving things into this equation, we have to make sure the units on our pressures match. Because again, they're dividing by each other. They just have to be the same units. It doesn't matter which ones we use as long as they're the same. So I know that 1 atmosphere is 760 millimeters of mercury, so I'm just going to use millimeters of mercury because then I don't have to convert. The other thing that we need to know is that our temperatures have to be in Kelvin, so I'm going to convert both of these to Kelvin, plus 273.15. Calculator time. 85.2 plus 273.15, 358.35. 95.6 plus 273.15, 368.75. All right, that's all I need. I can start plugging things in. I'm going to just color code this. P2 is 760. T2 is 368. Whatever is on the top part has to go in the front part. So the natural logarithm of P2 is 760 divided by P1 is 621. Oh, I have this upside down from what I did previously, but that's okay. So we have the natural logarithm of 760 divided by 621 equals negative x. And again, I'm leaving x in there as the delta H of vaporization, okay? 8.314 joules per mole Kelvin times 1 over. I'm double checking. I have 760 on the top, so I want the temperature that matches at 760. So 368.75 minus, I have 621 on the bottom, so I want 1 over 358.35. Sorry, I'm running out of room. Okay, so one thing, again, if you guys get to this point, you are more than halfway there, okay? One thing I'm already thinking about is in my head, I'm like, oh, this is an easy one. It's not, but like, we don't have to use E. One of the biggest problems I've run into with students is you guys panic about math and you're like, oh, well, I might have to use E somewhere. This doesn't need E. We don't need to take anything to the power of E. The natural logarithm of 760 divided by 621 is just a number. There's no variable in there. So I'm actually just going to do that on my calculator. I'm going to put in the natural logarithm of 760 divided by 621. Close parentheses, enter. I get 0.20199. And again, keep numbers. Don't round too much till the end. That equals negative x divided by 8.314. We'll deal with that. Times. And again, I'm going to just do this on my calculator. 1 divided by 368.75, enter, minus parentheses, 1 divided by 358.35, close parentheses. And I got negative 7.8703 times 10 to the negative fifth. Okay, now this is where, again, I start panicking a little bit. I've got negative signs and all kinds of craziness happening. So this is what I'm going to do right now to deal with my insane panic. I'm going to take both sides and multiply by 8.314. Multiplying by 8.314 gets it out of the denominator. So we've got 8.314 times 0.20199. Hold on a second. Okay, yes. I was just looking back at what I had written down, and I am still just absolutely praying I get this right. 1.679 equals negative x times negative 7.8703 times 10 to the negative fifth. Okay, so negative times a negative is a positive, and I'm just going to divide both sides by 7.8703 times 10 to the negative fifth. 1.679 divided by, that's not a negative. Oh, I don't think that was right. I'm just dividing it by the total because positive and a positive. So I'm just dividing by 7.8703. 703 times 10 to the negative fifth. Enter. I get an answer of, I get the right answer, 21,333 is what x equals. Now, be careful. That's not just what your answer is. We were trying to solve for the delta H of vaporization. Because our gas constant is in terms of joules per mole Kelvin, this is 21,000. Oh, and worrying about significant figures. 1, 2, 3, 1, 2, 3, 1, 2, 3. This is 21,300 joules per mole. That is the delta H of vaporization of this particular liquid. Most of the time, again, you will see it written in terms of kilojoules per mole. 21.3 kilojoules per mole. One thing I really want to point out is delta H of vaporization can never be negative. It is the amount of energy it takes to vaporize a sample. That is always going to be endothermic. That's always going to be energy required. So 21,300 joules per mole is a delta H of vaporization, also known as 21.3 kilojoules per mole. All right, my friends, I am going to stop there with the Clausius Clapeyron equation. Thank you so much. I feel like I'm on YouTube right now. I am on YouTube right now. If you have any questions, feel free to email me and let me know. Otherwise, hopefully I will see you guys. Well, hopefully I'll see you guys in class on Friday. Wednesday is canceled, and I still need to think about what I'm doing for Wednesday. All right, any questions, let me know. Otherwise, thank you so much.